I am not going to talk about polynomial optimization today. I'm going to talk about graphs and polytopes and other combinatorial things, which I think are also close to Monique's heart. And this is more recent things that I've been doing, so I'm personally excited about it, so I will talk about this, okay? So I'm going to talk about something called graphical designs. Okay, so this is a joint work with the people you see here. So graphical designs were defined by Stefan Steinerberger, who is my colleague at the University of Washington. He's a harmonic analyst. And on the left here is my student, Catherine Babecki, and the work I will present is joint work with both of them in different papers. Okay, so Stefan was motivated by the notion of spherical designs to create something called graphical designs. Let me quickly remind you or recall what a spherical design is, and then we'll use this, put this on graphs. Okay, so a spherical design is a quadrature rule. So it is a collection of points on the sphere, say x1 through xn, and they come with weights. So these weights are real numbers. Let's call them a sub I for each xi. And the property they should have is that if you have a smooth function f, sufficiently smooth, then the global average of the function on the sphere, which is what you see on the left, is the same roughly as the weighted average of the function values at these points xi. Okay, so that is a quadrature rule. And of course, huge staple of numerical integration. You know, people really like these. On the sphere, the right functions you want to integrate are the spherical harmonics. The spherical harmonics are homogeneous polynomials graded by degree, but they are harmonic, meaning that they are annihilated by the Laplace operator. And spherical harmonic means they're actually eigenfunctions of the Laplace operator. Okay, so you can just think of them as polynomials if you like. And then because of the grading, there's a natural order in which you want to integrate. You want to catch as many polynomials, you want to catch as high a degree as you can among the different polynomials, okay? So this definition, spherical T design, means that you have a design that integrates all polynomials of degree at most T, all spherical harmonics. And on the picture here, you see a spherical 5 design. So these are the vertices of a regular icosahedron that's inscribed inside the sphere. And if you just take the function values there with uniform weights, then you will get the same thing as integrating the, any polynomial of degree up to 5 on the entire sphere. Okay? So this is the notion of spherical design. And so what Stefan decided was he wanted to put this on graphs. He had already figured out how to do this on other manifolds like tori and so on. So he decided to put this on graphs, and so let's do that. Okay, so for this talk, I'll keep the graphs very simple. Let's take them to be finite graphs, simple, connected, and very soon I'm also going to assume regular, but none of this is really required. The theory is very general. And so now we have a function on a graph. So like this f function over here, that just means I have a function on the vertices of the graph. I have some real numbers on the vertices. And we say that a set W of the vertices, subset, with some weights, which I'll call AW, they average the function if you do the same thing as we saw before. So on the right here is the global average of the function on the graph. And I want that to become equal to this weighted average over the W vertex. Okay, so we're interested in sets like this W with the weights. Okay, so here's a quick example. So here's the Peterson graph, and here you see a function on the graph. If you quickly add up these numbers, you'll see they're 0. They add up to 0. So the global average of the function on the graph is 0. And on the left here, you see one design, these red dots with uniform weights. And if you just add up the weighted average, you'll see 2 minus 2 minus 1 plus 1. It also adds up to 0. Okay, so on the left is a uniformly weighted design. And on the other side, which is hard to see with the colors, is not uniformly weighted. So now I have some weights that are 1/3 and then another weight that's 1. And it's depicted by these pink colors, which are difficult to see, and then this is the 1. So the pink is the 1/3. So this is a slightly smaller design because I'm allowing non-uniform weights. And again, the weighted average over those points is 0. Okay, so this is the notion of a design. This is the notion of average. I haven't quite defined design yet. I'll talk about the functions in a second. Okay, I haven't told you which functions we're going to do this for. So I'm just giving you one example of a function and something that averages it. Right. So yeah, good question. So the next question we can ask is, which functions do we want to average? So in the case of spherical designs, it was the spherical harmonics. And so the natural guess here is, let's work with the eigenvectors. Let me go back, yeah. So I'm going to use so the natural thing to do here is work with the eigenvectors of the graph Laplacian. Because in the spherical case, we were taking eigenfunctions of the Laplace operator. So now let's go to the Laplacian of the graph. But because I'm going to assume that my graph is regular, it doesn't matter whether you use the Laplacian or you use the adjacency matrix or a scaled adjacency matrix or whatever. The eigenstructure is the same. The eigenvectors are the same. So in this example, let's go with not in this example, for the talk, let's go with trying to average the eigenvectors of AD inverse, where A is the adjacency matrix and D is the diagonal matrix, whose diagonal entries are the degrees of the vertices. Okay? But this is a regular graph, so this is just a scaled identity. Okay? So we're going to average these eigenvectors. These are the functions that I will take, and that's enough because it's an eigenbasis. So any function is a linear combination of these, so it'll be enough to do that. So one special feature about this particular matrix is that this is doubly stochastic. So the rows and the columns sum up to 1. So because of Perron-Frobenius, we know that means the spectrum lies between -1 and 1. Okay? The biggest eigenvalue is 1. It's always attained. I'll call this the trivial eigenvalue. And then all other eigenvalues have absolute value less or equal to 1. Okay? So the spectrum lies inside this interval. Good. So here's an example. So here's the icosahedral graph on the left here. And in this case, this has 12 vertices. So we expect 12 eigenvectors. And they're also orthogonal because my matrix is symmetric. I can choose an orthogonal set of eigenvectors. So here they are. So in the rows of this table here, you see the different eigenvectors. This number phi and the number psi are these irrational numbers that you see up there. Okay. In this example, you see immediately that there are 4 eigenvalues, and they come with multiplicity. Okay. So they do lie between 1 and -1. The first eigenvector that comes with eigenvalue 1 is always the all ones vector. So that one is trivial. And all the other eigenvectors, all the other rows of the matrix, because of orthogonality, they have this property, right? 1 transpose times any other fj is equal to 0, okay? But this is very convenient because this quantity is also the global average of fj, right? So if I want to take the global average over the whole graph, I'm just doing 1 transpose fj because I'm just adding up all the values. So this is very convenient because now the global average of all these eigenvectors except the first one is 0, okay? So I don't have to think about what that number is anymore. All right, so this is good. We have all the eigenvectors. So the last thing I need to tell you is what order should we try to do this in, right? So before we had this natural order given by the degree of the polynomials. Now I don't have any such natural order. And the order I'm going to use is the one that you see here. So if you notice the way the eigenvalues are written, they're written in decreasing order of absolute value. So the first one is 1. Then these two eigenvalues tie in absolute value, so you can break the tie any way you want. But the next one is definitely smaller. Okay, so we're going to put them in decreasing order of absolute value. And this order is actually kind of natural for the analyst. So at least for Stefan, this was natural. He calls this the frequency order. And I'll try to motivate this just with some examples of why this is. So this order is supposed to capture the smoothness of functions on a graph. Okay? So here's a picture of the United States graph. This was apparently made by Donald Knuth, this graph. So recently, there was a short article by Catherine in the AMS Notices, and Knuth wrote to her and told her that this graph was his. So we know now this is made by Donald Knuth. Anyway, so this is from Mathematica. It's one of the built-in graphs in Mathematica. So what's going on here? So we have a vertex for every state, and there's an edge that connects to vertices if the state share a border. And here, for instance, this is not a regular graph, so the first eigenvector is not trivial. So you already get some information there. And here's the first eigenvector. So the colors show you the different magnitudes of the numbers. And you see it's fairly smooth as you go across the graph. That's the first eigenvector. Then here's the second eigenvector, also still fairly smooth. The ordering of the eigenvalues are like this. Okay, so we are ordering the eigenvalues by absolute value. And now if we go further, so here, for example, you see the 11th eigenvector, and you see this jumps quite a bit. Okay, so the smoothness is nicely captured by this ordering on the absolute values, on the eigenvalues given by absolute values. So we call this frequency order. And the general idea is, like in Fourier analysis, if you have a relatively smooth function on your graph, meaning the function value doesn't change too much when you jump from one vertex to the adjacent one, then you expect that most of that function is made up of these low frequency eigenvectors. So we would like to catch as many of the low frequency eigenvectors as possible in this averaging game. Okay, so this is one natural ordering. In this combinatorial setup, it doesn't matter which ordering we use, but I will use this ordering in the talk. Okay, so this is called frequency order. Yeah, question? Yeah. When you get which one? Like the negative one. Say, oh, you mean all the way to -1? Yeah, it's not exactly a precise theory. So it's sort of respecting the structure of the graph. So for example, if you had a bipartite graph, then you would have eigenvalue 1 and eigenvalue -1. And in that case, this picture would look exactly like one color on one side and another color on the other side. But it does respect the structure of the graph. So it's sort of smoothness modulo the structure of the graph, roughly. It's not a very precise theory, okay? But generally, this is the type of picture you will see, that the smoothness is captured by the ordering of these eigenvalues. Okay, so we have this notion. So here now I can define what a graphical design is. So the definition goes like this. So we start with this graph and we order the eigenspaces. So these big lambdas are the eigenspaces. And let's assume that there are m distinct ones. So the graph has n vertices, but there are m distinct eigenspaces. And I'll always assume that the trivial one is the first one. But after that, you can put it in any order. For the most part, I'll do this in frequency order. Okay, so we order the eigenspaces. And then a K graphical design is some subset of the vertices W with weights that averages the first K eigenspaces. Okay, so we want to capture entire eigenspaces at one time because we don't want to worry about which eigenbasis we're using in each eigenspace. And also, this makes sense when you have eigenvalues with multiplicity. This makes better sense than to go eigenvector by eigenvector. Okay, so this is the definition. And this is due to Stefan. It's actually from like 2018, but the paper appeared in 2020. Okay, so having made the definition, now you can worry about different types of weights. So there are different types of designs. So if the weights are just any real numbers, then I'll just call it a weighted design. This is not so attractive for people who do quadrature. They don't like negative weights typically. More interesting or much more interesting for them would be positively weighted designs, so where the weights are non-negative. And then if you're a combinatorialist at heart, then you might look for a 0-1 weight or a uniform weight. And in reality, you'll see that this last one, while it's very appealing combinatorially, it's quite restrictive. And so the middle one seems to be the right balance. Okay, so we want to look for non-negative weights, and that can average the first K eigen spaces. Okay, so that's a K design. So here are some examples. So back to the icosahedral graph, and here I've ordered the eigenspaces like this. So before I had them ordered in frequency order, now I jumbled it up a bit. So lambda 1 is still first, then I put the last one next, and so on. Okay, so it's some order. And then on the left here, you see a arbitrarily weighted design. So this one has both negative weights and positive weights. The negative weight is blue. The non-negative weights are pink or red, depending on the magnitude. Okay, so that's one. And here's a positively weighted one. It needs more vertices because I'm putting more restriction on the weights. So that one requires 9 vertices, whereas the first one only required 7 vertices. And then finally, here is a combinatorial design. And this combinatorial design actually cannot average the first 3 eigenspaces. It can only average the first and the second, okay? In fact, there's no combinatorial design that can average the first 3 eigenspaces. So this is why what I mean by it's more restrictive, like you don't want to insist that your weights are uniform, okay? So this is an example of these designs. Okay, so last definition is oftentimes we're also interested in what's called an extremal design. So these are designs that can catch all eigenspaces except the last one. Okay, so you decide the ordering first on the eigenspaces, and then we say we want to get everything except the last eigenspace, and you cannot have any proper subset that can average all eigenspaces. So this is a fact. So this is the best you can do, these extremal designs. And of course, this depends on the ordering you put on the eigenspaces, and this was defined by Konstantin Golubev in 2020. And he makes some nice connections to graph theory, like to graphs that meet the Hoffman bound and Cheeger bound and so on. So he has a very combinatorial paper on these extremal designs. Okay? Right, so let's come to the questions. So the questions we wanted to ask at the beginning was, can we compute these? How do we compute these K designs? Can you compute the smallest K design? That would be most interesting. And then maybe more ambitiously, is there a way to organize all these designs in some clever way? Okay. So again, if you sort of remember the formulation a little bit, or maybe I'll just say it, is that so computing these designs, depending on which kind of weights you're looking for, is either a linear algebra question or a linear programming question or an integer programming question. But as soon as you say that you want the smallest, then you're putting sparsity on top of that problem, okay? So then the problem becomes hard because even finding a sparsest vector in a subspace is difficult. So even the linear algebra version becomes very hard as soon as you ask for smallest, okay? So we thought about this for a long time, didn't make any progress. But then at the end of the day, we figured out that there's a way to do the last one. So there's actually a structure on all these designs, which is maybe a way to optimize. So let me explain that theorem next. Okay, so here's the main theorem. This is, I'll call this the structure theorem. So we proved that the minimal positively weighted K designs. So from now on, I'll mostly only talk about positively weighted designs. So minimal means that it's minimal by inclusion. So minimal positively weighted K designs are in bijection with the facets of a polytope. Okay, so there is a polytope you can construct so that the facets contain all these minimal positively weighted designs. And the bijection is sort of complementary. So if you have W, a K design, then V minus W, the complement of W, are the vertices that index the facet, or they're the indices of the vertices on that facet, okay? So you'll see many examples. So if you want a small design, if you want W to be small, that means you want V minus W to be large. So we're looking for facets of this polytope that has lots of vertices. In fact, the maximum number of vertices. So how do you do that? How do you find facets and polytopes with the maximum number of vertices? That's really the equivalent question to sparsity, okay? So if we wanted sparse things on the left, we're looking for facets with the maximum number of vertices, okay? So here's a little cartoon that shows you, it's not a cartoon, it's actual picture of designs in the octahedral graph. So these are some extremal designs in the octahedral graph, and you see the polytope is a triangle. Facets all have the same dimension on the polytope. Right, so by facet, I really mean the maximal dimensional faces. okay? So all the faces do index designs, but the minimal ones are indexed by facets. So in this picture, you see the facets, which are the lines. They index the minimal designs, but if you go to the vertices of this polytope, which are faces, they will also index designs, same type of designs, but they're not minimal. They contain more vertices. Okay. So this is the theorem, and so I mostly want to just illustrate this theorem on a few examples, just so you see how the theorem works, okay? So I won't say much about the proof, but here is an illustration of the theorem. Okay, so first of all, let me give you a recipe to construct the polytope, and then we'll see examples, okay? So these polytopes are known as eigenpolytopes. A version of them, or at least the version we need, is a slight elaboration of what's originally called eigenpolytopes. They were defined by Chris Godsell, who's a graph theorist from Waterloo, in his thesis from 1978. And the recipe is like this. So suppose I want to average the first k eigenspaces. Then I break up, so this matrix here is the full matrix of eigenvectors. This is a square matrix. And the matrix is banded according to the eigenspaces. Okay? So suppose I want to average the first k eigen spaces. Then I have one set which I'll call k that contains lambda 2 up to lambda k. So ignore lambda 1 because lambda 1 is special. So put lambda 1 with the complement. So I have k, which is lambda 2 to lambda k, and then k bar is everything else. Okay? And then we color the entire eigenvector matrix according to the ones we want to average and the ones we don't want to average. Okay? So the blue ones we want to average, these eigenspaces. The pink ones are the complement. Okay? Now we split this matrix apart into two parts. The pink ones go up there and the blue ones go down there. Ignore the blue, go to the pink part. So this is the part that we don't want to average, okay? So that's I'll call this UK bar. And now switch from the rows of this matrix to the columns of this matrix, okay? So that's some configuration of points that live in space. And then we convexify those points. That is this polytope, okay? So graph theorists do this. They do construct this type of polytope, but they don't do it for multiple eigenspaces. They usually do it for one eigenspace. And this has some important consequences in spectral drawings and things like that. So people who are interested in this, Godsell and his collaborators have several papers on these eigenpolytopes. Here, the slight variation is that we're stacking eigenspaces together, okay? So this is the recipe. So we take the part of this matrix that we don't want to average, put it together in a matrix, and then take the columns, convexify. That's the polytope, okay? So now let's see an example. So here's back to the icosahedral graph. So in this graph, say suppose I want to average lambda 4 and lambda 3, which are here. So if we ignore this, and then take the parts we don't want to average. So lambda 2, I don't want to average. That's this band. But we always throw in this all ones vector on top. Okay, you'll see why in a second. And now we take the convex hull of this part, the pink part that you see here. Okay, so you can ignore this one, the first row, because it's just embedding the whole thing in at level 1. So ignore that. So what we expect is some three-dimensional polytope, right? Because these are all three-dimensional vectors. So I expect that. And if you do the convexification, then by miracle, you get the icosahedron again. Okay? So this is a miracle of graph theory. And there's a reason for it. The people who study eigenpolytopes understand this. But you do get the icosahedron again, which is coincidence. And now my theorem says that the facets of this icosahedron index the minimal designs that can average these three eigenspaces, lambda 1, lambda 4, and lambda 3, okay? So let's just check. So every facet in the icosahedron is a triangle. So the complementary set is the design. So in this example, I can draw the graph and the polytope all together because I got the icosahedron again. And the complementary set, which is colored here in the back, you see, is a design that can actually average the first three eigenspaces, okay? So lambda 1 is counted with the bad part, with the pink part, but everything can average lambda 1, so it doesn't really matter, okay? So these are this is how you construct the polytope. Let me do one more maybe. So here's the icosahedron again, but with frequency order. This is the usual order that we like. In this case, if we want to average the second and third eigenspaces, then we have to convexify this bottom part. Okay, so take the vectors in the bottom part. We expect a 5-dimensional polytope with 12 vertices. But if you look closely, you'll see that all the vectors are doubled. So this vector appears 2 times, this one appears 2 times, and so on. Okay, so the vectors are doubled. So you end up with only 6 vertices and a 5-dimensional polytope. So that's just the 5 simplex. Okay, but there are 2 elements sitting at every vertex. So every facet has actually 10 elements because there's 5 coming from the facet of a 5 simplex, but there's doubling going on. So there's really 10 elements. So the complement is 12 minus 10, which is only 2. Okay, so the designs in this case have size 2. So as soon as you change the order, the size of the design changed, and here you see the design. Okay, so this is the recipe. And this doubling is pretty dramatic. So for example, in this next example, which is the truncated tetrahedral graph, if I look for an extremal design, meaning I want to average everything except the last eigenspace, now we expect an n-gon, right? We expect a 12-gon. This thing has 12 columns. But if you look carefully at this picture a little bit more, you'll see that every column appears 4 times. So instead of getting a 12-gon, you actually just get a triangle. But every vertex now carries 4 indices. So if I want to get a design, then if I want to get a minimal design, I look at a facet. I look at the indices that are complementary to it, which is this, 2, 5, 8, 10. And here you see the minimal design. Okay. So this is the theorem, that there is a polytope that organizes all of these designs. And now using this, you can do various things. So, okay, so before I go any further, let me just say one word why this works. So the proof behind this is oriented matroid duality or Gale duality. So if you've seen it before, then all we're doing is using this dual set of vectors. So I want to average the blue ones. The blue ones are really the eigenspaces that I wanted to catch. But it turns out that what are called positive circuits in the blue side are exactly the positive co-circuits on the pink side. So there's some duality going on, and that's really what's happening here. Okay. So usually Gale duality, so Gale duality is actually quite old. I recently discovered it's actually due to Strum from the 1800s. They call these associated sets in classical algebraic geometry. But in the world of polytopes, it really appeared in the work of Perles and Grunbaum. It's written in Grunbaum's book. That's the main place. I think that's one of the older references for this. And typically in the polytope world, people use Gale duality to find interesting polytopes using the blue side. So using what's called the Gale dual, okay? For us, the designs are living in the blue side, and we're using the polytope to tell us about the designs. So we're using Gale duality in the reverse direction to say something about the designs just by looking at the combinatorics of the polytopes. Okay. Right, so now once we have this theorem, we can get various consequences. So let me just summarize the different consequences. One of them is, of course, this structure, this polyhedral structure. This allows you to put bounds on the sizes of designs, because if you have a polytope like this, say it has dimension d, then you know that every facet is at least a simplex. So we know that it has at least d vertices on it, which means the design is at most n minus d in size. Okay, so that's really Kara theory in action. It's not a very fancy statement, but it puts a size on the design, but it also shows the existence of these non-negative designs for all values of k. Okay, so this was not known before that they exist, but this proof will show you that. And the other thing that it does is it puts this sort of adjacency structure on designs, right? Because designs are sitting on the facets of the polytope. So you can take the edge graph of the polar polytope or just walk along facets and you get this graphical structure on designs themselves. So here, for example, is the Peterson graph. This is just a local picture. So this is one vertex of the of the graph, and then here are the neighboring vertices, and then sitting on all the edges, you see the non-minimal designs. And this goes on. Okay? This is just one vertex picture. And it shows some interesting things, like you see, this is a combinatorial design in the middle, but it's surrounded by non-combinatorial designs. So you can sometimes get these disconnected parts. Okay. So that's one consequence. And another consequence is this allowed us to actually do some optimization. Because once you have this polyhedral structure, you can study the polytope and then tell which is the smallest design. So we did this for 3 families of Cayley graphs, because one of the difficulties here is to know the eigenvectors when you want to do families of graphs. And not a lot is known about eigenvectors. So lots of people know lots of things about eigenvalues in spectral graph theory, but eigenvectors are more rare. But for Cayley graphs, they're okay because they come from the characters of the group representation. So we know the eigenvectors. So we did it for some families, like cocktail party graphs are the same as edge graphs of cross polytopes. So that one was easy. Cycles are also easy. Graphs of the hypercubes, we don't know the final answer. We don't know what's the optimal extremal design in frequency order. But in this case, what really helps is the theory of codes. So you can show, for example, that Hamming codes are very good designs. And there are some some generalizations of Hamming codes that are also very good designs. So these are all just linear codes. They form very good designs. Here, the polytope theory was not that useful. It was more the coding theory that was useful. Okay, so you can optimize through this method. And then lastly, the last application I want to mention is the work with Stefan. So this has sort of a small but kind of cute application to random walks. And so here's what it is. So if you remember how you do a random walk on a graph, we start with some initial probability measure. Let's call it mu0. It starts in one vertex, let's say, and the walk starts to move. And as you move, you get other measures. So at the kth step, you will get a measure mu k plus 1, which is gotten by applying AD inverse to mu k. So by iteratively running AD inverse, multiplying AD inverse many, many times, you propagate the walk. And then this fact here is very well known, that the distance between the kth measure and the uniform measure, or the stationary measure, is controlled by lambda 2, the second eigenvalue of the graph. Okay, this is a classical result. So you can ask, okay, what about all the other eigenvalues? Are they just completely useless, or do they have something to do with random walks? And it turns out through designs, you can extend this theorem to all eigenvalues. Okay, so here is what the result is. So it says that if you pick any k between 1 and n minus 1, then there is some initial measure that is supported on at most k vertices. So instead of starting with one vertex, allow yourself 2 vertices or 3 vertices or k vertices. If you do that, then you can always find an initial measure such that the convergence rate to the stationary distribution is controlled by lambda k plus 1. Okay? So for example, and what this measure is one of these positively weighted k designs. So if you start your random walk on one of these designs, so here's an example. So in this graph, for example, there are 18 vertices. Lambda 2 in absolute value is 0.75. So if you started the usual random walk, it would be controlled by 0.75 to the k. But if you take another eigenvalue like this one, lambda 11, it's only 0.25. And now the theorem will say that there is some vertex set containing 10 vertices, such that if you start your random walk there, then it will converge at this better rate. But it turns out, because designs can have smaller size than the expected size, you can just start on these few vertices. I think here there's just these red vertices, 5 of them, 1, 2, 3, 4, 5, 6 of them. So if you start on these 6 red vertices, then you'll get a random walk that decays at rate given by 0.25. Okay? So it extends that theorem to all eigenvalues. So you can imagine, like, again, in the bipartite graph, the random walk doesn't usually converge. It just jumps from one side to the other side. That's because the second eigenvalue is -1, whose absolute value is 1. But if you go to lambda 3, which is smaller, and you're willing to start on 2 vertices, then it will converge. Okay. Yes, yes. So, I mean, you'll have it, yes, so this just comes from the general theory again. You will get. So in this one, we changed I changed a little bit, which I put under the rug, because now we are actually integrating eigenvector by eigenvector, not eigenspace by eigenspace in this theorem. Okay, so it's a little simpler than doing eigenspace by eigenspace. Yeah, so that's basically Farkas' lemma. So there's a little lemma you can prove that there always exists a measure that's going to be orthogonal to the first k eigenvectors. So that was Farkas' lemma. And yeah, it was very interesting writing a paper with the analysts, because for them, Farkas' lemma was really hard. And for me, everything else was really hard. So anyway, it's Farkas' lemma, the existence of such a measure. And so, but once you have the measure, then you can put it together in this theorem. Okay, so that's the last consequence, I think. Here's just a picture of a big design. It's from this article that Catherine has in the notices. Yeah, we were just looking for big data, and here's one. And that's it. Yeah, so these are the papers that I talked about. There's also this gallery of designs. If anybody is interested in contributing, please write to Catherine. It only has combinatorial designs right now. So there's many, many interesting questions to work on. Okay, thank you.
So there are bounds for the size of a spherical design, for instance. So do you also have some sort of bound for an optimization bound for the size of a graphical design?
Yes. So it's basically so that the bound is given by the existence of the polytope. So the polytope facets index the minimal designs, right?
Yeah.
And the relationship is complementary. So if the design is W, then V minus W are the vertices that live on that facet. That's the index set. So because if I create a D-dimensional polytope through this process,
yeah,
I know that the facets have at least D vertices on it,
yeah,
right? So that means the design has at most N minus D elements in it. Yeah, so that's the bound.
But this is okay. So, but it may be difficult to see how many things you. But I mean, like there is no like easy to solve optimization problem like for a spherical design that you can just solve this problem and it gives you a bound that you don't have to know this polytope or something like that.
So you don't even need to know the polytope, because the polytope is gotten by convexifying that pink matrix, right? Yeah. And because that's an eigen, those are all independent vectors, yeah, the dimension of that polytope is just the number of rows of that matrix. You don't even need to construct the polytope.
I see.
So the bound is easy. It's really just Carathéodory if you work on the blue side. It's just telling you that there's a cone, and if you pick a point in it, then it needs at most dimension many things. So that's easy. But what's not known is basically how much smaller you could go. You could have much smaller designs than that bound. And it's actually NP hard to check whether there is a smaller one.
I see.
But it can exist, much smaller ones, like we saw in the icosahedron.
I was thinking more of a lower bound, actually. But we can.
Yeah, lower bounds can be trivial.
Yeah.
You could have just one vertex that can integrate quite a few. Yeah. Again, if we go to combinatorial designs, it might all change. So I'm talking about the mostly non-negative designs. So there it's really linear programming with the sparsity thrown on top. But if you go to combinatorial designs, I think you'll get non-trivial things.
So there's some non-existence result that spherical 7 designs don't exist. But here, I guess you can have these extremal m-1 designs. Is there some bound that says when the number of vertices is bigger than a finite number, those also don't exist?
No, they always exist.
They always exist.
Yeah, but the combinatorial ones not.
Okay.
So that maybe, I don't know if that's the right analog, but the positively weighted ones always exist because the polytope exists. So this was the fact that was that helped Stefan figure out this random walk thing, because without that, he knew that there's some measure that could have negative and positive weights that will do the right thing. But now that we know they always exist, that you can actually do it for a probability measure, not just a, signed measure. So the positively weighted designs always exist for any K, but not combinatorial designs. And that I don't know much about either.
Wait, so do there exist combinatorial designs in the hypercubes? I'm sorry. if you
Yes,
mentioned
in the
they do.
hypercube they exist all the way. In any ordering of eigenspaces, they exist. The extremal ones exist.
Wow.
So there cannot be anything that integrates all eigenspaces except the full set of vertices. That's a fact that you can write down because of the orthogonality of the eigenvectors. But you can ask for extremal, meaning that all eigenspaces except the last eigenspace. That
still exist.
combinatorial ones exist for the cube.
Okay.
Yeah. In any ordering of eigenspaces.
David behind you.
Yeah, to find the weights, do you solve an LP feasibility problem?
Yeah,
or-
it's essentially you have to solve an LP feasibility problem.
But it doesn't come from the theory, the weights. It doesn't say anything about it.
It
Just
do-
says they exist.
It does come from the theory, because if you are willing to accept the oriented matroid duality, actually, what did
Maybe.
these are all the slides I didn't want to show. Okay. Actually, maybe that slide is useful, the one for your question. Yeah, so here, for example, is Gale duality. This is something I skipped because I thought it would be technical. But here you see the polytope comes from convexifying these columns, and the designs come from circuits on this matrix. So that means minimal dependencies. So if you solve for the minimal dependency, that vector is the weight. So if this is u, and I solve u times little a equal to 0, then that little a is the weight vector. Correct.
Okay, thank you.
So it is an LP, I guess. So Monique's question was whether she said that for spherical designs, the weights come from orthogonal polynomials and the points, the design itself. And is there a link to orthogonal polynomials? I'm not sure. So I don't know if the graphs are just completely different kinds of objects or what would be the analogous thing. Not sure. I think what would be interesting is to understand some sort of limit theory. So as you let the graphs become really, really big on a manifold, does this actually limit to something that looks like spherical designs? This would be interesting, but I don't have any clue on how you do that. Yeah.
If there are no more questions, let's thank Rekha again for the wonderful talk. And